Like a lot of people, I love me a 3D printing time-lapse, and I've experimented with a few different options for capturing them over the years. But I've struggled to get a camera mount for the moving bed of my Prusas that I was really happy with. The combination of that plastic cantilevered arm and the heated bed have just proven to be suboptimal. Poor things get a bit flaccid. But I think I may finally have something that's gonna work out for me. And all it took was combining generative design and laser welded aluminum powder. Okay, I may have gone a smidge overboard with the fun tools to solve a problem that's, let's face it, already solved a few ways over. But what can I say? Sometimes I guess it's more about the journey than the destination. Although I do like finding excuses to play around with these kind of tools, I did have a reason for choosing to use one for this particular project. Generative design combines some form of simulation with an optimization algorithm to produce geometries that can maintain stresses and deflections within limits while using the bare minimum material. But what I really love about using generative design tools, in addition to the cool shapes they make of course, is that I feel like they force me to focus time up front on defining my functional requirements. Things like what's attached to what and where. Do these interfaces have to have any specific features on them? What are the loads and constraints I think the interfaces will see? Any keep out areas for things like tool access or cable routing or moving parts that need clearance and all that kind of stuff. I think it pushes me to keep more of a big picture perspective on the design in a way that I think is a great reminder more generally for me. And if nothing else, it makes for some unique looking CAD files. Yep, this beaut of a model was the CAD work for my end of the camera mount. As a reminder, here's another look at what this turns into. Yeah, that makes sense. So, what is it we're looking at here? Let's start with these bits shown in green. The green highlighted parts are the included bodies, the ones I want to be included in the final part. These are also the bodies I'll be applying loads and constraints to later. In this case, the included bodies are the camera mount point here and the two bed attachment points here and here. The bed attachment points will replace the 6mm long steel standoffs on the Prusa that separate the Y carriage from the heated bed. Unfortunately, the center-to-center spacing between them isn't symmetric, so I chose a slot one to make it a little more flexible. The camera mount's basically a thick washer for a 1/4-20 fastener. My plan is just to attach a GoPro mount to the surface here. It would have been cool to print in the GoPro mount geometry like I did with this previous build, but I just wasn't confident enough in how that might come out without having to run through a few iterations. Plus, going with a 1/4-20 mount point allows me to easily swap out the GoPro for something else down the line if I want. So, interfaces out of the way, on to the big ass red thing. The red designates obstacle geometry, or as I tend to think of it, keep out areas. This is where I'm telling the software it's not allowed to add any material. For example, around my spacers, the Y carriage and heated bed take up the space above and below the spacer, so I need to make sure the mount doesn't interfere with them. So I just went with big blocks above and below. The only other obstacle bodies are the three to maintain the clearance holes for the fasteners going through the mount points. And that's pretty much all there is for the CAD side of the project. The next step is to take these geometries and tell the software what kind of loads they should handle. To do this, I first need to answer the question myself, so I started by getting a mast for the GoPro and some mounts. Then I made some assumptions on the accelerations I expect. 1G for gravity, 1G for stage movement, which is like 10 times the accel limit on the Mark IIIs, and a half G side load to account for some light jostling when handling. And then I doubled each of these, and that's both to be a bit conservative and to account for the fact that these loads should really be applied through the center of all that mass, so there's a moment and or offset that I'm just really not including, so extra G's all around. Then a little help from Newton got him into force values that I could apply to the camera mount. Then it was back over to the bed mounts to apply some constraints. And while clamping the bed spacers between the bed and carriage will technically create constraints on all 6 degrees of freedom, only frictions constraining the rotations around the fasteners and any side-to-side movement on the slotted side. So I let the x-axis, the one in the direction of the slot, be unconstrained on the slotted side. That should ensure the solver will leave some stiffness in this direction between the two legs. Now that the geometries, loads, and constraints are all defined, all that's left are things like setting the material and manufacturing settings. That part just involves clicking through a bunch of windows, so I'm going to save you from watching that, but if you're interested, I'll include the riveting details in the article linked in the description. Once all that's done, it's time to click solve and get to waiting. You can see how the software starts out with this lovely blob, filling most of the space I've allotted to it. And then it just starts to carve away material, iteration after iteration, until it hits either the maximum allowable stress or the minimum thickness in every bit of material. Or at least that's the idea. But you can see it doesn't do this with just a single design. Instead, it's working through a handful of designs in parallel. My assumption is that each of these variations is the result of some difference in initial starting conditions the software uses, but I'm not really sure. Looks like we got a winner on every attempt. How about that? Since they all seem comparable, I just opted to go for the 4 recommended designs, exported each one to step, and is ready to get them made. Unfortunately, I'm just a tad shy of the $500,000 and up price tag for a selective laser melt machine, but apparently PCBWay wasn't. And then they were awesome enough to send me these parts free of charge if I'd let you fine folks know this is where I got them. Talking about an easy decision. Hey, I got these at PCBWay. Okay? Even though they sent them to me on the house, I was definitely curious what their prices are like for SLM parts, and was very pleasantly surprised that I could have had one of these for under 40 bucks. We had some SLM tools in my last job, and you couldn't even get them to put powder in the damn thing for under $1,000. I think it's just unreal that stuff like this is now becoming available to us home gamers. Living in the future is awesome. If you haven't encountered selective laser melt, aka SLM, it's pretty amazing. It works by laying down thin layers of powdered metal, and then laser welding patches at a time to build up 3D parts. I'll include some links below to others who have done a much better job of explaining the details than I ever could. But anyway, yeah, I uploaded the step files, chose aluminum after hovering over the titanium button for a bit. Then, a couple weeks later, I was opening them up like a kid at Christmas. You may have noticed that I only have 2 printers, but got 4 mounts. The other 2 are for breaking. But before I broke anything, I wanted to check a few things to see how close the printed parts came to the nominal design. I started by tossing each of them on the scale, comparing each against what Fusion predicted, and they all came out within a gram of what was expected. I'll take it. Then I broke out the calipers and took a look at the thickness of the bed mounts. They each came out about 100 to 150 microns, or 4 to 6 thou, oversized. And I found a similar result when I took a look at the thickness for the camera mounts, as well as for the outer diameters. So my hunch is this 100 to 150 microns of overprinting is somewhat uniform across the part. Not awful, and I can definitely plan around that in future builds. Then it was finally time to see if I could get some stiffness measurements. Unfortunately, my load tester is still very much a work in progress, and I don't yet have encoders of the like up and running, so I had to toss together this lovely little sensor to measure deflection of the part during loading. It uses the same basic concept as the displacement sensor I showed in my last video, but it has the added perks of a precarious razor blade and sketchy wiring. This was also the first time testing out some new code on the tester. I figured odds were 50-50 that the little sensor got sliced in half. But I was pleasantly surprised to have the tester behave itself, and the little sensor survived to measure another day. The big white ball you see sitting on top of the mount is just a Delrin ball. Putting the ball between the load plate and the mount gives me the defined placement of the load that's easier to duplicate in the simulation. Once I had things set up and confirmed the code was working, I had it run through quite a few cycles, collecting a whole bunch of load and displacement data as it did. And here are the not so pretty results. Ta-da! I was still able to get some reasonably repeatable results, and I got an average of about 32 newtons per millimeter, plus or minus 3. Oh, and you may have noticed that I loaded them up to 25 newtons, which is quite a bit more than the 5 newtons I designed to. Okay, so the code wasn't working perfectly. But it was in time to see what the simulation predicted, so I updated it to go through the same 25 newton range and hit submit. And while I was waiting, I sliced that ugly little bastard just for fun, which at least took some of the sting out when I tossed those sim results into the previous stiffness plot. The predicted stiffness was 68 newtons per millimeter, which is a little over twice what I'd measured. And while auto-meshed finite element models have a tendency to overpredict stiffness, I think the larger culprit here is likely more to do with my fixturing. In hindsight, an aluminum extrusion probably wasn't the ideal choice for load testing an aluminum part, but yeah, live and you learn. Overall, I'm really happy with my new mounts, and I'm looking forward to a good many time lapses thanks to them. But if I had to do it over again, there are a couple changes I'd make. The main one would be to move the camera a little further away from the print bed. I was just worried about how much cantilevered load the bed could take, but I've now done some tests with a GoPro positioned a good 30 millimeters further out with no issues. As it is, it's possible for the camera to collide with the part cooling fan during bed leveling, and an extra 15 to 20 millimeters of breathing room certainly wouldn't hurt. So I went ahead and ran a few of these with additional offsets, and I'll include those along with the original models at the links in the description. The other change would be to try and integrate some sort of a tip tilt head into the mount. It'd probably be fine to use some plastic printed parts for this one, but it'd be kinda cool to have tip tilt as part of the metal print, right? Anywho, that's all for this one. Huge thanks again to PCBWay for these parts. I'm genuinely excited to know that cost-effective metal printed parts are now an option for future projects. Happy building!